We're going to introduce you to a famous problem called the traveling salesperson problem, otherwise known as TSP. And what the traveling sales problem does is it answers the following question. Given the list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city and returns to the original city? You imagine something like this would be applicable in today's world with Amazon packages. I have so many Amazon packages, and here's all the places I need to go. I do need to return the truck to the garage, so I have to go back to the exact same spot. Where should I go? What would be the fastest and most efficient path to take? This was a problem that was originally faced by a traveling salesperson, but it's relevant to many, many areas today, including routing data around a network, manufacturing microchips, observing locations with a telescope, or even sequencing DNA. In all of these situations, we want to find a solution that has the most efficient path between multiple locations. My husband works for Best Buy, and they have what's called supply chain management, and that's where they're trying to ship their products out. And how can they get their products out in the most efficient way? That's the traveling salesperson problem. I think this is a really simple problem to solve because obviously you're just going to calculate all the distances and then find the shortest path. But when you are programming an algorithm or a computer to do that work, what the computer is going to do is loop through and find every possible combination and then compare those values to find the shortest. So here's an example of what our computer is doing, is if I give it 4 different destinations, A, B, C, and D, the computer is going to check each of those paths, all the different combinations or permutations of the directions that you can go or the stops you can make in different orders. And it's going to calculate all of them, and then it's going to find the best path. Now you'll notice here we have 2 that are the best path, and they just happen to be the reverse order of each other, so they look the same. I can change this, and again, it does it pretty quickly with 4 destinations. The calculator is going to calculate all 6 different possible orders that you can go in, and then it will figure out which one is the fastest. Example with 5 cities. So with 5 different destinations, you can see that the total number of options is quite a bit longer. I'll show you the result or how many in total in just a moment. But again, the the computer has to go through all of these different possible options before being able to determine which one is the best. Here's how many you get if we are using 6 cities. You can see again, the list starts to get fairly long, and we only have 6 cities. Think back to that example I showed of the 46 different cities in Germany. We are with 7 cities. So again, look at all the possible different combinations, permutations, orderings that a computer would have to loop through to check in order to confidently be able to say which is the best. Similar to what we were seeing with that exponential growth when we were doing the group raffle, what you'll notice here in the traveling salesperson problem is that we have a factorial pattern. What a factorial is taking a number and multiplying it by all the numbers that come before it. So for example, 4 factorial would be 4 times 3 times 2 times 1. This factorial pattern is actually n minus 1 because we already know our starting point and our ending point. So when I have 4 cities, it's actually 3 factorial, which would be 3 times 2 times 1, or 6 paths. 5 cities would be 4 factorial, which gives us 24. You don't need to remember this formula whatsoever for the traveling salesperson problem, but what you do want to recognize is how crazy these increase, right? So when we had 7 cities, there were 720 different possible combinations or permutations of those cities, orderings of those cities, I keep mixing up my words, that the computer would have to loop through and check. If we did this with the 46 German cities, it would take approximately 3 to the 37th years in order for a computer to figure out that many possible different paths that that salesperson could take. This is just unreasonable. We can't have a computer running that and taking 3 to the 37th years to find the answer. is where heuristics come into play. Heuristics is basically common sense. It's where we find a good enough solution to a problem when finding the actual solution is just impractical or possibly impossible. That's fun to say. So when we use heuristics, you consider how you yourself would approach the problem. I bet a lot of you during this traveling salesperson problem were thinking, well, why do I have to check every possible option when it would just make the most sense to go to the closest option from where I am? And that's what a heuristic is. A heuristic is using common sense and how you would approach the problem versus checking every possible answer because that, or possible solution, because that would take way, way, way too long. A common heuristic, which is actually the one that's used in the traveling salesperson problem, is called the nearest neighbor. The computer will just always pick the nearest unvisited city as the next city on the path. So instead of checking every possible option, it's just going to the next nearest. This will give us an approximate solution, but it's not always going to be 100% the best solution. In fact, on average, these heuristics end up being about 25% longer than the shortest path possible. But you get an answer, right? An approximate solution is definitely better than no solution at all. In the next following slides, what you're going to look at is some places where you're going to see some heuristics used in other areas of life. Some other common problems where heuristics are used. You're going to read through these and jot some notes down in your note packet. After looking at those examples, there is a video you will find that's going over a problem called the halting problem. The halting problem is an example of a problem that is just completely unsolvable. Make sure you watch that video and get some key takeaways so that you understand the basics of what an unsolvable problem is.